India's journey towards self-reliance in air combat technology reached a landmark chapter with the Aeronautical Development Agency's latest initiative, a comprehensive DFMA designed for manufacturability and assembly analysis package for the AMCA stealth fighter program. With ADA floating a detailed work package covering the DFMA evaluation of nearly 2,000 distinct components and structural assemblies of the advanced medium combat aircraft, the nation is embarking on one of its most complex, scientifically demanding, and strategically critical engineering campaigns in recent history. DFMA, widely regarded as a cornerstone of modern aerospace product development, integrates two technical disciplines, design for manufacturability and design for assembly. Its central premise is deceptively simple: engineer aircraft parts so they are both easy to manufacture and straightforward to assemble, cutting costs, errors, and delays. However, when the platform in question is a fifth-generation stealth fighter like the AMCA, complexity rises exponentially. Every component must marry unprecedented aerodynamic performance, radar-absorbent stealth characteristics, extreme structural integrity, and thermal management with the ruthless pragmatism of mass production and assembly line repeatability. The ADA work package, issued for competitive participation by Indian vendors, lays out a 24-month milestone-based roadmap. The assignment is clear: scrutinize, simulate, and optimize every element of the AMCA's architecture: fuselage frames, composite wing spars, actuators, engine mounts, undercarriage struts, weapons bays, avionics enclosures, sensor housings, and more. This initiative doesn't just require textbook DFMA analysis. It asks partners to interpret ADA's updated standards, simulate every production challenge, evaluate alternatives, and model the impacts of design changes on overall system performance and risk. The first technical hurdle arises from the sheer granularity of the task. The AMCA, envisioned as India's answer to global platforms like the F-22, F-35, and Su-57, is constructed from thousands of parts, many made from advanced composite materials, titanium alloys, and radar-absorbent structures. These materials often demand specialized handling. For composites, manufacturability analysis means understanding vacuum bagging, autoclave curing, resin infusion, fiber layup orientation, joint bonding, and out-of-autoclave options. Every ply stack in composite skins affects not just aerodynamic flow and RCS radar cross-section, but the shop floor: how easily workers can cut, lay, cure, inspect, and repair these materials. ADA's standards require vendors to demonstrate not only technical feasibility, but also compliance with reliability, non-destructive evaluation, NDE, and rework cycles. Titanium and high-temperature alloys present their own set of obstacles. Used extensively in engine housings, high-stress joints, and reinforcement brackets, these metals resist corrosion and fatigue, but are notoriously difficult to machine and weld. ADA's DFMA package demands deep analysis of CNC milling strategies, tool path optimization, heat treatment, and additive manufacturing overlays. Vendors must model the impact of cutting speeds, coolant technologies, burr mitigation, and in-situ measurement. In addition, powder bed fusion and directed energy deposition techniques for additive parts must meet rigorous tolerance, grain structure, and fatigue life criteria laid out by ADA. In the context of stealth design, it's not simply about strength. It's about minimizing joints, fasteners, and surface discontinuities that can betray aircraft location to hostile radar. DFMA also imposes a structural logic on all design teams: reduce part count, eliminate unnecessary fasteners, standardize interfaces, and simplify subassemblies. This runs directly into the challenge of stealth integration. For example, weapons bay doors, RAM, radar-absorbent material, coatings, leading-edge control surfaces, and embedded antennas must be built to millimetric tolerances and often cannot be standardized using off-the-shelf practices. ADA's package instructs vendors to use digital twin simulations, predicting not just manufacturing bottlenecks, but also field service requirements, repair scenarios, and logistics implications. Failure to do so risks delays during airframe integration or vulnerabilities found only during flight testing. Engine integration remains a major technical challenge. The AMCA's airframe must seamlessly house both indigenous and imported propulsion options. Engine mounts, thermal blankets, intake geometries, and afterburner assemblies must be accessible for inspection and maintenance while retaining stealth contours. AMCA DFMA protocols require Indian vendors to model not just first-time production, but also in-operation disassembly and repair, factoring in tool clearances, vibration damping, corrosion pathways, and fluid line routing. For maintenance engineers, a poorly designed fastener or access panel could mean dozens of extra man-hours per year. For pilots, it could mean the difference between mission success and catastrophic failure. Avionics and sensor integration places the project at the cutting edge of electromechanical DFMA. The AMCA suite includes AESA radars, IRST sensors, data link arrays, missile warning systems, and secure data buses. Each must be mounted inside electromagnetic interference-shielded bays, surrounded by cooling loops and secure cabling, all while minimizing mass and bulk. ADA's work instructions presuppose hundreds of vendor-specific DFMA scenarios, such as PCB stacking, EMI gasket placement, solder quality checks, and modular plug-and-play harnesses. Indian suppliers face the dual challenge of mastering aerospace-grade electronic packaging and adapting rapidly to new indigenous systems as national technology matures. The weapon bay structure forces a marriage between aerodynamics, stealth, and DFMA. Sliding doors, rotary launchers, ejectors, hydraulic lines, and sensor wiring all crowd limited space, demanding compact modular assembly solutions. Designers must model not just actuator reliability, but also what happens if field repair is needed after a hard landing or battle damage. ADA's standards specify failure case simulations, rapid part replacement designs, and repair accessibility, all while maintaining flush outer contours. The result is a series of iterative design loops. Every change in assembly logic may ripple through radar cross-section tests and high-speed wind tunnel trials. Perhaps the most transformative technical milestone is the use of advanced digital engineering. ADA's project expects vendors to use state-of-the-art tools for CAD, finite element analysis, FEA, computational fluid dynamics, CFD, parametric modeling and process simulation, digital twins, automated assembly modeling, and VR-based ergonomics checks ensure that every part and process is virtually tested before a single real component enters production. This closes significant historic gaps that earlier Indian programs, such as Tej's Mk1, faced, where unmodeled assembly problems led to costly rework, delays, and performance compromises during squadron induction. The challenge of knowledge transfer looms large. Most Indian vendors, while technically sophisticated, lack continuous exposure to fifth-gen stealth fighter requirements and global best practices in DFMA. To address this, ADA's program includes regular knowledge sessions, supplier peer reviews, and joint risk analysis panels. Vendors must document not just their DFMA findings, but also their process improvements, test failures, and benchmark comparisons. The feedback loop is dynamic. ADA retains oversight and injects new requirements as global standards shift, and operational learning accumulates from AMCA prototypes and other stealth aircraft worldwide. Supply chain resilience underpins the program's industrial logic. Indian manufacturers, long at the mercy of imported fasteners, chemicals, sensors, and composites, must now localize production for hundreds of unique part types, merging local innovation with global certification. The DFMA package includes extensive risk modeling. What happens if a supplier fails, if a material is delayed, or a batch is rejected due to microstructural flaws? Vendors simulate alternatives, prepare contingency plans, and engage with ADA's central logistics grid. For India's dream of indigenous fifth-generation manufacturing supremacy, this layer of planning is as vital as the design itself. The program faces hurdles not only in technical execution, but in timing and synchronization. The 24-month deadline is aggressive for a project of this scale. Vendors must run parallel tracks, design iteration, process simulation, supply line establishment, and regulatory compliance, often for the first time. Periodic cross-vendor stress tests will ensure no core supplier falls behind and that integration bottlenecks are resolved before full-scale initial production begins. ADA's standards demand continuous reporting, early flagging of latent risks, and a process of rolling gate reviews at each milestone. The final challenge is operationalization. The DFMA analysis is not a theoretical exercise. Its fruits must translate into real, flyable jets meeting all mission specs, cost projections, and reliability targets. Indian vendors must develop first-pass yield plans for every assembly, minimize rework rates, and anticipate the realities of field deployment, squadron sustainment, and combat sortie preparation. ADA, leveraging lessons from both Indian and international platforms, expects every simulation, assembly plan, and correction to be documented, peer-reviewed, and validated in prototype and low-rate initial production cycles. In summary, the ADA work package for DFMA analysis of AMCA aircraft parts is not just a contract award, it is the crucible for India's fifth-generation ambition. Covering nearly 2,000 parts and assemblies, from stealth skins to powerplants, avionics to weapons, the program fuses cutting-edge science with the demands of mass production, cost control, and operational reliability. The technical developments include mastery of composite and metalworking, advanced digital engineering, integrated supply chain management, and relentless process optimization. The hurdles, material science limits, vendor experience gaps, time constraints, and the constant challenge of stealth versus manufacturability are formidable but not insurmountable. The result, if successful, will be a world-class example of Indian aerospace engineering, delivering powerful, stealthy, and cost-effective fighter jets for the future battlespace.